Hello everyone, welcome to the video. Today we are going to discuss the problem binary tree right side view. In this problem, we are given a binary tree as input and we have to return the list of nodes that we will see if we stand on the right side of this binary tree. For example, in this binary tree, we have to return 1, 3 and 4 because these are the nodes that we see when we stand on the right side. We are going to solve this problem today. We will go through the thinking process, we will write the algorithm, and we will also see a working code for the same algorithm. But before we start, if you are new to this channel, please don't forget to subscribe. Let's start. To begin with, let us first note down the key things given in the question. We are given the root of the binary tree, and we are told that we are standing on the right side of that binary tree. We have to print the values of the nodes that we can see from the right side, and we have to return such values ordered from top to bottom. So if we consider this binary tree as an example 1, 2, 3, 5 and 4, then from right side we will see these three nodes. So we have to return 1, 3, 4. So if we consider our solution to be a black box, we are getting an input as tree node root, and we have to return a list of integers. What is tree node? This class is also given to us. It is a class which has three things: a value, for example 1 here, a pointer to tree node left child, and a pointer to tree node right child. For example, a pointer to 2 and a pointer to this 3. This class will also have constructors here, but this class is given to us. So what will our function signature look like? Our function signature will look something like this. Let's start thinking about the problem. So the first approach that comes to mind in questions of binary tree is of tree and recursion. What do we do in this approach? In this approach, we think that okay, we have to find the answer for this whole tree, whose root is this first element. Now, if somebody magically provides the answer for this smaller tree, which is rooted at the left subchild, and this another smaller tree which is rooted at the right child, if somebody gives us answers to these and these, can we derive the answer for the whole tree? Let's see. Our aim is to find the right view of binary tree. So we may think that the relevant subtree might be this. Now, if somebody provides us answer to this subtree, then can we use that answer to figure out the answer for this whole tree? It may seem like yes, that for this subtree answer will be 3 and 4. So we will get 3 and 4, and we will just add root here, and our overall answer will become 1, 3 and 4. So our approach may be just get the answer for the right child. But that is not always the case. That will not work always. Let us assume that this node was not there. Now let us think whether our approach of considering the answer only for the right child will work or not. It won't work. Why? Because if we consider the answer for the right child, that is the right view of the right child, it will only have 3. It will not have 4 because that node is not present. But if we stand from here and look onto the tree, then in our view we will have 1, we will have 3, and we will also have 5. If we are considering only the right child view, then we won't be able to have 5 in our answer. So this approach will not work always. Now that we know that simple tree and recursion approach won't work always, we will have to think of some other approach. Let's start thinking about the problem again. Now our aim is to find the right view. That is, we have to return the elements 1, 3 and 4. Now what can we see about these elements? We can see that if these are the 3 levels of the tree, level 1, level 2 and level 3, then the 3 required nodes are the rightmost elements of every level. So we make an observation here that we have to find the rightmost elements at every level. Now how do we do that? we can traverse this tree level by level. That means we first traverse and get the elements here at this level, which is 1. Then we traverse on this level and get the elements here, 2 and 3. Then we traverse at this level and get the elements here, 5 and 4. And at every level, we just note the last element of that level. So we make other observations as well, that we will have to traverse the tree in level order fashion, and for every level we have to note down the last element somewhere to be able to return our answer. Now, how do we traverse the tree in level order fashion? Consider ourselves at any arbitrary level. Let's say we are at this level. Now, if here we have to first print 5 and then we have to print 4. Now, we know by common sense that if we are at the element 5, it is very difficult for us to directly reach the element 4. The parent pointers are not there and there is no direct connection between 5 and 4. That means we cannot reach 4 from direct tree-like linkages when we are at 5. That means if we have to print 4 after 5, it must have been coming from some data structure where 4 was already stored after 5. So we note here that the nodes at a particular level will have to be in some separate data structure that will be like a list. What exact data structure we don't know yet, but it will be something like a list where after 5 we will have the 4 element present, since we don't have direct access to 4 from 5. That means it would be present in some other data structure. Now let us see what will happen at the next level. At the next level, this 5 may have its children, the 4 may also have its children. So what should happen ideally in our answer? After 5 and 4, we should have children of 5, A, B, and after A, B, we should have children of 4, C, D. But we can access A and B only when we are at 5. So what we can do, that once we have visited 5, then before visiting 4 from this data structure, we should try to put the children of 5 into this data structure. Behind 4, we will not be visiting the children, but we will just be putting it in data structure behind 4 so that we can visit A and B after we have visited 4. So our data structure would look something like this. 5, after 5 it will be 4, after 4 it will be A and B, the children of 5. And in this manner, in this order we will be visiting 5, 4, A, B. What should be the next element that we should visit after B? It should be C. But how will C and D come into this data structure? When we have visited 5 and then we come to visit 4. Now before visiting A and B, we will put 4's children into this data structure as well. So our data structure would look something like this. First we will visit 5 and put its children in the data structure. Then we will visit 4 and then put its children in the data structure. And we would have removed 5 and 4 as well. So what kind of data structure does it strike to us? It simply looks like a queue, because the element that comes first into the data structure gets taken out first. So now we know that with the help of this queue data structure, we can traverse our tree level by level. But we also need to do this third thing. We have to note the last element at every level. Now how do we know what is the last element at every level when we are dealing with this queue? We can only know this when we compare the levels of the two elements. And if we see that, hey, its level is greater than the level of our current element, that means this is our element that should be part of our answer. But the tree node, these all have data type tree node. Tree node does not contain the level information. It contains only 3 things: the value, the left child and the right child. Therefore, in the queue, if we directly put tree node, our problem will not be solved. So we will have to declare a new kind of data structure, queue node. This queue node will have both the information, the tree node and the level. Therefore, whenever we say that we are inserting a node in a queue, we will not be inserting the direct tree node. Instead, from that tree node, we will be constructing something called as queue node, and we will insert that queue node into this queue. And whenever how will we know the level? We know what is our current elements level. So its children's level will be just the current elements level plus 1. So now we know that we will have this tree. We will use a queue and a queue node kind of data structure to traverse this tree in level order, where we will have the level information as well. And for every level, we will note our last element in some data structure. Therefore, to note the last element in some data structure, we need another data structure. That data structure will contain only the result. It could be another data structure, a list of integer. So we have everything that we need to get the right view of binary tree. We only need to convert our thoughts into an algorithm. Clearly, we need a list of integer result variable. It will store our final result 1, 3 and 4. We also need a new class queue node. It will have two variables, tree node and level. We also need a queue of queue node which has to be declared. Now how will it be initialized? To initialize it, first of all, we will only put the root element. So we will write here queue.add. We will construct a new queue node from our root node and we will put level is equal to 1. Therefore, in this we have this new queue node that corresponds to first node of the tree, and we put that into the queue. Now what do we need to do? Clearly, we need to take out every element of the queue and insert new elements in the queue in every iteration. That means we have to iterate. And till when we will iterate? We will iterate till queue is not empty, because queue not being empty suggests that there is at least one node that we have not visited. So we will have a while loop here and we will iterate till queue is not empty. In every iteration, we will get the frontmost element in the queue using queue.poll. So we get the frontmost element. What is its data type? Its data type is queue node. Now what do we need to do? We need to add its children into the queue as well. But to get to its children, we need to first get its tree node. So we get the tree node here. Then we can simply add its left child and its right child, whichever are not empty, into the queue. But we have to keep in mind that in the queue, we will have to add them as queue node instances. So for every tree node, left child and right child, both of them, we will be constructing a queue node instance and then we will be adding it to the queue. Adding left child and right child to the queue will ensure that we are traversing the tree in level order. But we have to do one more thing. We have to check if this current element is starting a new level. And how will we check that? If the level of the current element is greater than the level of the previous element that we had seen in the queue, that means this current element is starting a new level. Consider here, if we have come here 5, its level will be 1, 2 and 3. Its level will be 3. Now 3 is greater than 2, which was the previous element, 3 here. Therefore this is starting a new level, and therefore we should note down this previous element because that will be part of our result. This means we need another variable, previous element, to track the previous element. Now before we start, we can have an imaginary previous element with a null tree node and level equal to 0. And in every iteration, this current element will become previous element for the next iteration. For example, here if we consider if we are at 3 currently, the previous element is 2. But when we come at 5, the previous element will be 3. When we come at 4, the previous element will be 5. Therefore, in every iteration, our current element will become previous element for the next iteration. But before it does, we will have to check if this current element's level is greater than the previous element's level. And we need to not consider this imaginary element, so we will have to check that previous element's level is not equal to 0. If this condition is satisfied, that means this current element is starting a new level, and we have to add the previous element in our result. To do that, we will have to get the tree node from the previous element. So we get the previous tree node using .get tree node, and we add this value in our result. Now we have to return this result, but we have to do one more thing. When, let's say, this tree ends at here, ends at 4. Now there will not be a new level starting, but 4 is also our part of the answer. So we will have to add this 4 separately here. Since there will be a new level, no new level starting, there will not be any element in the queue, but this last element will not become part of the result. So we will have to add that separately, and then we will have to return the result. So this completes our algorithm of finding the right view of binary tree using this level order traversal. What will be the time and space complexity of this algorithm? The time complexity will be big O of n, where n is the number of nodes in the tree. Why? Because every node in the tree is traveled just once. Therefore, time complexity is big O of n. Space complexity is also big O of n because we are using this queue, which will have the elements of the order of n at any point in time. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function that takes tree node root as input, that is root of the binary tree as input. And root of the binary tree as input means we have the whole binary tree as input because we can access the whole of binary tree from this root. So it takes this binary tree as input, and we have to return a list of integer. We have to return a list of integer value of the nodes that are seen from the right side of this binary tree. So first of all, we have a very basic condition that if there is no tree, there is no list to return. So we return an empty list. Then we declare a variable result that will store our final result. Then we need a queue. Now queue is needed. Every element of that queue will be of the type queue node. Now what is queue node? Queue node is another data structure. So here we define a class queue node. What does queue node contain? It contains the tree node and it also contains integer level of that node. So we have a constructor here to construct queue node, and we have getters for level and tree node. This is our class of queue node. So we have here declared a queue of queue node. And how do we initialize it? First of all, we put our root element into the queue. Then we know that we need two more variables, current element and previous element, because we will be comparing the levels. So we have to initialize an imaginary previous element to the root. Imaginary previous element to the root can be constructed using a new queue node with node value as null and level value as 0, if we are considering root at level 1. Now we have the previous element ready. Now we will start traversing from the queue. So we will iterate. Now in every iteration, we will be pulling out the first element of the queue. But we will iterate only till queue is not empty. That means we have visited all the elements. So what do we do in every iteration? We first pull out what is the current element. Then we also figure out what is the level of the current element. We can simply use a get level to get the level here. And we can also get the tree node for the current element by using get tree node here. Now what do we have to do? First of all, since we are traversing the tree in level order, we have to check if the left child and right child are not null. If they are not null, then we have to insert them into the queue. So we first check if the left child is not null, then we construct a new queue node. We construct a new queue node by providing the tree node as the left child and level as the current level plus 1, and we add that to the queue. Similarly, we add the right child. Now, till this part, we have written the code to traverse the tree in level order. But now we also have to note down the last elements of every level. So how do we do that? We see if this current element is starting a new level. So we need to compare the current element's level with the previous element's level. So we get the previous element's level. And here we check that if the current element's level is greater than the previous element's level, that means current element is starting a new level. That means previous element was the last element in its level. Therefore, we have to add the previous element's value in the result. But how do we get the previous element? We will get the previous element's tree node by using the method getTreeNode, and we add that value to the result. And at the end of iteration, very important, we assign the current element to our variable previous element, because in the next iteration this current element becomes the previous element. So we iterate in this manner and we accumulate all our right view elements in this result. But the last element that we will encounter, below which there is no level, after which the queue has become empty, that means we would not have added that into the result, because we are able to add something to a result only when we have visited the next element to that result. But if we are at the last element, then there is no next element, so we would not have visited that. So we will have to add that last element here, and last element would be there in the previous element. So we add previous element dot get tree node dot value in the result, and then we return the result. So this completes our code for right view of a tree using the level order approach. So our first approach to solving this problem was the level order traversal of the tree and noting down the last element. So we have solved this problem using this approach. Now let us try to solve this problem using another approach. For that, let us again start thinking about the problem. We have to traverse this tree such that we have the rightmost element at every level. So let us try to see that what happens if we start from the root and always move rightmost possible. If we keep traversing in this manner, then we will have the rightmost element at every level. But then it is possible that we don't have a right child here. What to do then? If we don't have the right child here, then the rightmost possible path is going through this left child. At this level, this will be our rightmost element. So what we are essentially doing at every node is we are trying to traverse right, and only if the right child is null, we go left. But even when now we are at this position, we will again follow this philosophy. We will try to traverse right. This way, at every level, we will note the rightmost element. We can keep a note of them in a list. But will this approach be enough to find what we are looking for? In the initial part of the video, we discussed a scenario where if this node 4 was not there, then we would not be able to take this 5, and this 5 was the rightmost element at this level. This means only traversing right at every node is not sufficient. We will have to traverse left as well. It is possible that the left subtree is actually deeper than the right subtree. Then there will be new levels on which there are rightmost elements which we have not yet discovered. Therefore, whenever the right child will be done, we will have to traverse the left subtree as well. And in the left subtree as well, we will be following this philosophy only. The step 2, we will try to go to the rightmost points only. But for any level, let's say at this level or this level, we have already seen what are the rightmost elements. We don't need the rightmost elements in this tree at these levels. We only need the rightmost elements in the new levels that we have not discovered so far. That means when traversing the tree, we also need to keep track of what is the level that we have seen so far, what is the maximum level that we have seen so far. Therefore, this is our fourth observation, that we have to track the max level that we have seen so far. And whenever we are at any node, we can see that if this node's level is greater than the max that we have seen so far, it is part of our solution. So we can see that we will be using recursion here. Now let's say this was our recursive method. What all inputs will it need? First input that it will need is the node itself, because only then we will be able to traverse right or left. Then we know that we have to maintain max level seen so far. So this will also be an input. Let us consider an arbitrary data type for now to track this max level seen so far. Why have we used an arbitrary data type here and not just an integer? We will discuss this in some time. Then, since we have to compare at every node whether its level is greater than the max level that we have seen so far, that means we need another variable that denotes the level of the node. So we have int level. Then we need to store our answer in a list of integer. So a list of integer result will also be passed. Now let's see what will happen in every recursive call. So first of all, for the current level, we have to check whether this current level is greater than the max seen so far. If the current level is greater than the max level that we have seen so far, this would mean that at this level, this is the first rightmost node that we have seen. So we will add that to our result. Then we have to update our max level as well, because now we have a new max level. Then, as per the observations here, we will first try to go rightmost. So if the right child is not null, then we will go right to the node's right child with level +1 as input. And if this is null, only then we will go to the left child. Then the left child's recursive call will again land upon this method. And again, as we thought that we want the philosophy of step 2, it will again try to go in the right direction. Therefore, this method seems to be working. And finally, our answer will be stored in this result that we can return. Now, coming to the tricky part. How are we tracking max level? We can see that the max level we are not tracking as an integer, but as another data type. And why is it so? The thing about max level is that its value will be constantly updated, and every recursive call should have the access to the updated value of max level. Now what will happen if we pass this as an integer? We are talking now in the context of a programming language like Java. In Java, let's say we track max level by an integer and we pass this integer around. Then here, when we will do this max level is equal to, let's say 3 + 1 4, then it won't happen that the value at this place will change and the max level will now point to the new value. This is not something that's going to happen, because in languages like Java, arguments to a method are passed by value. So when we pass this integer, int integer, or even integer class max level integer, then this reference is not passed. Instead, a copy of this pointer is created and that is passed here. So this copy is local to this method. So when this 3 will get updated to 4, now when we will call this recursive method, this local copy's value will be passed. That means another max level which is pointing to a different place whose value is 4 will be passed. Now it may seem to work fine as we stay in the same recursion path. But when this recursion path ends, let's say this method ends and we come down here when we have to go to the left, then at that point in time, this max level will not be pointing to the latest updated value because only the local copies have been passed in the recursive method call. It will still point to this old value. So this won't work. So how do we solve it? We solve it by using another data structure. Let's say that data structure that we define is this class max level seen so far. It has only one member, integer max level, and it has getter and setter methods. So now instead of passing as integer, we will pass this as a reference of this data structure. We will pass it as an instance of this data structure, max level seen so far. Now what will happen here? Here while updating, we won't be updating this reference. So it won't happen that a new pointer will be pointing to somewhere else. Instead, we will use the methods of this object, getter and setter, to change the value here. So it will always be acting on this same memory position. And so this will work. So this completes our algorithm for the recursive approach for getting the right view of the binary tree. What will be the time and space complexity of this algorithm? The time complexity will be big O of n. Why? Because every node will be traversed just once. And the space complexity will be constant, big O of 1, because we are not using any data structure that is proportionate to the size of input. But a space complexity would arise because of the recursion. Since every method call occupies some space in the memory, and with the recursion there will be multiple method calls. So about of the order of height of the tree, that space will be occupied in the memory. Let us now go through the code for the same algorithm that we just discussed. You can also find the link to this code in the description. So this is our main function that takes tree node root as input and will return a list of integer as output. The list of integer will be the values of the nodes that can be seen from the right side. So first of all, a very basic condition that if the root is itself null, then we have to return an empty list. Then we declare a result variable, a list of integer that will store our final result. Then we know what is our approach. We will have to traverse the rightmost possible, and we have to keep track of the max level seen so far. So if we have any element at a level that is that level if we have not seen, then that element will be the rightmost element and we have to take a note of it. So in the recursive method, apart from the tree node, we will also be passing this result as input, and we will also be passing a max level seen so far variable that is used to keep track of what is the max level seen so far. And since we also need the current node's level, we will also be passing the current level here. Now, how are we tracking max level seen so far in this new data structure? Let's see. So this is our class max level seen so far. It simply has one member, integer max level. Now this has a constructor, and this also has a getter and a setter method. That means we can set the value of max level. This is the most important thing that distinguishes it from passing an integer or int primitive. Why? Because when we will be changing the value of max level using this setter method, we will be changing the value at that memory location itself. While if we were passing an integer, then a copy of that reference would have been passed. So it would be a local copy to every recursive method, and we would not have the same value updated always. So let's see how does this recursive method work. Here in the recursive method, clearly we have decided that we will first traverse right. So if the right child is not null, we traverse right. How do we traverse right? we pass the right child as input. Since the right child is at another level, the new level will be current level plus 1, max level seen so far, and result. And only if the right child is not null, then we will go to the left child. But also, if the right child is done, it was not null, and we have seen everything around the right child, then we have to traverse the left child as well. Why? Because it is possible that for the left subtree, the left subtree's depth is greater than the right subtree's depth. Therefore, left subtree may give us the levels that we have not explored so far yet. So we will then traverse the left subtree as well. And in the left subtree, again we will pass node.left, current level plus 1, max level seen so far, and result. Whenever this left subtree will be called again in that left subtree also we will try to go towards the rightmost only. And only when the rightmost is either null or is done, we will move to the left child. Now let's come to this part. Here we check if the node that we are visiting right now, its level is greater than whatever the max level that we have seen so far. Now since in this way of traversing, we have ensured that we are always visiting the rightmost element of a level first. That means this is the rightmost element at this level. So we add that to the result. And we also update max level seen so far. Note how we are updating max level seen so far. We are setting the attribute of this object. If this would have been an integer and we update that integer here, then it would not have worked. Let's say we would have updated it to the value 4. Then we would call this recursive method with value 4. And again, this would come here. Let's say we updated it to 5 and then 6 and so on. We keep on calling. Here, only a copy of this reference is being sent. So this will be passed with the copy, which will be pointing to 4, 5, 6 and 7. But when this side is done and when it is the turn of this side, then this value would not have been reflecting the 5, 6, 7, whatever is updated. It would still reflect the 3 because a copy is being sent and not the actual reference. Therefore, we needed this another data structure max level seen so far. So this way we will have our answer in this result list and we can return this. So this is our code of printing the right view of a binary tree using a recursive traversal approach. This is it for this video. If this video was useful to you in any manner, please let us know by commenting below. Also let us know in the comments what will be the next problems that you would want to see on this channel. Please don't forget to like and share the video and subscribe the channel. We will meet again in the next video with some other problem. Thanks for watching.